A piece of breakfast cereal shaped like a shell, a loop, or a star did not get that shape in an oven. It got it from a hole and a knife. In the standard technical description of food extrusion, a soft mixture of ingredients is forced through an opening in a perforated plate called a die, and that die is cut to produce the required shape. What emerges is then sliced to a specific size by blades. The machine doing the pushing has its own name, an extruder, and so does the mixture moving through it, the extrudate. Many breakfast cereals are made this way, so the question worth answering is narrow, and the evidence can close it. What does that machine actually decide about breakfast, and what does it quietly rule out? Start with what the process was built to promise. Food extrusion is described as a way to enable mass production through a continuous, efficient system that delivers uniformity in the finished product. Read that carefully, because uniformity is not a side effect of the machine. It is the stated point of it. A batch oven produces a population of slightly different objects. A continuous extruder is designed so the 1,000th piece matches the first. That single design goal explains a lot about the modern cereal aisle, where the promise on the box is not surprise but repetition. The same shape, the same size, the same behavior in milk, every box, every year. The machine that makes that promise possible is not a baking innovation. It is a forming and flow control innovation. Now the constraint, which is where the machine starts making decisions instead of just following orders. An extruder, as described, is typically a large rotating screw fitted tightly inside a stationary barrel with the die at the far end. Everything about that arrangement demands one thing from the food. It has to flow. A mixture that will not move as a soft, coherent mass under pressure cannot be pushed through a shaped opening at all. There is a second version of the process, and it matters. In some usage, extrusion means extrusion cooking, where the food is cooked by heat as it is squeezed through the die. Forming and cooking stop being two stages. They become one continuous event inside a steel barrel, measured in the distance between the screw and the knife. The simpler application came first in the sense of ambition, not necessarily in chronology. Extrusion as pure shaping, without cooking in the barrel. The documented list is familiar and mostly unglamorous. Pasta, croutons, breadsticks, and flatbreads. Pre-made cookie dough. Sausages. Look at that group and you can see the logic clearly. Each one is a food whose identity is largely its shape and its cross-section. A tube, a stick, a sheet, a cylinder in a casing. For those products, the extruder is a shaping tool that replaces hands, rollers, and molds. And the cooking happens somewhere else, later, in a boiler or an oven or a smokehouse. At that stage, the machine is a very good sculptor. It is not yet a cook. The turning point is heat inside the barrel. Once the same screw and die assembly cooks while it forms, the catalogue of what it can make changes character completely. The products attributed to extrusion cooking include many breakfast cereals and ready-to-eat snacks, confectionery, some baby foods, full-fat soy flour, textured vegetable protein, some beverages, and both dry and semi-moist pet foods. That is not a list of similar foods. That is a list of entirely different aisles built on one shared mechanism. A breakfast cereal, a meat substitute, and a bag of dog food are not culinary relatives, but they can be manufacturing relatives. The moment cooking moved inside the machine, the extruder stopped being a piece of equipment that served a recipe and became a platform that recipes were written for. Here is how that platform works, end to end, in the terms the sources actually support. Ingredients are mixed into a soft mass. The rotating screw carries that mass forward inside a close-fitting barrel, building pressure. Heat is applied as the material is driven through the die, which cuts the outline. Blades chop the moving extrudate into individual pieces. Nothing stops. That continuity is the whole economic argument, because a continuous line does not lose time loading, unloading, and resetting between batches. Follow the chain that machine sits inside, because an extruder only makes sense as one link in it. Upstream, the line demands raw material that can be mixed into a soft, coherent mass, and the documented pattern is that extruded foods usually carry a high starch content. That points the buying side of the business toward bulk starch-rich inputs rather than delicate ones. In the middle of the chain sits tooling, the perforated plate, the die cut to the required shape, the blade set to a specific size. Those are metal parts, and they are the link that carries product identity. Downstream, the same barrel and die architecture feeds markets that have nothing else in common. Ready-to-eat snack lines, confectionery, some baby foods, textured vegetable protein, some beverages, and both dry and semi-moist pet food. One equipment platform, several separate distribution networks drawing on overlapping inputs. What these sources do not give is the geography. No growing regions, no freight routes, no shelf life figures. I can describe the chain of transformation with confidence, from mixed mass to cut piece to finished category, and I am not going to sketch the map of fields and warehouses from memory. It is worth noting where the same vocabulary shows up elsewhere. In plastics, extrusion molding sits alongside injection molding as one of the most common industrialized forming processes in an equipment family that grew out of rubber machinery and metal die casting, developing rapidly from the inception of polymer injection molding in the 1870s through the 1930s. Those dates belong to plastics machinery. The sources here do not date the arrival of extrusion in cereal plants, and I am not going to borrow one timeline to fill the gap in the other. The cost of the process shows up in the ingredient list, and it deserves precise language rather than alarm. Foods manufactured by extrusion usually have a high starch content. That is a documented pattern, and it is a manufacturing observation, not a health verdict. What it tells you is that the machine exerts a kind of selection pressure on formulation. If a food must become a flowing mass under heat and pressure, hold a shape as it leaves a die, and survive a knife, then materials that behave that way get used and materials that do not get left out. The visible variety on the shelf, then, is largely a variety of dyes and formulas running on the same fundamental line. A brand's signature shape is, in engineering terms, a tooling decision. Change the plate at the end of the barrel, and you change the product identity without changing the process at all. Two cautions keep this honest. First, the family resemblance to plastics is a resemblance in principle, not proof of a straight technology transfer, and this evidence does not establish who borrowed what from whom. Second, extrusion is not one machine behaving one way everywhere. Helical extrusion in the plastic pipe industry feeds granules such as polyethylene or polypropylene into a unit that mixes to a formula and lays a profile helically onto a preheated rotating mandrel, and that production is described as discontinuous. Food extrusion is described as continuous, so the shared word covers processes with opposite rhythms. And there is a real open question here that the sources do not answer. Why starch-heavy foods dominate extrusion output? The correlation is documented. The causal explanation is not in this evidence, and treating my own reasoning about flow behavior as a finding would be overreach. What survives all that caution is still substantial. A single forming principle, a screw turning inside a barrel against a shaped opening, underlies breakfast cereal, snack food, confectionery, some baby food, textured vegetable protein, some beverages, and pet food. That is the scale claim I can defend, and it is not about tonnage, it is about breadth. The same mechanism spans human breakfast and animal feed, infant nutrition and candy. When one machine architecture reaches across categories that share no culinary tradition, the machine has stopped being a tool used by an industry and started being a condition the industry designs around. So the answer to the opening question is this. The extruder does not just make cereal faster, it decides the terms, it rewards ingredients that flow, shapes that a die can cut, and pieces a blade can separate cleanly, and it delivers uniformity because uniformity is what a continuous line is engineered to produce. The bowl on the table is downstream of a die plate. That is the trade-off at the center of this system. The thing that made consistent, ready-to-eat breakfast possible at industrial scale is also the thing that narrowed what breakfast could physically be. The next question follows naturally, and it is answerable with the right documents rather than assumption. Which came first in that shared lineage of screws, barrels, and dies, the pipe or the puffed grain? Visual reconstructions are illustrative. Facts and interpretations are based on the sources listed in the description.